Itamar, what's GM mean? Good morning. Good morning. I see. I know it. I know GM more as general manager, like in sports, or grandmaster when it comes to chess. That's what GM means to me. Trying to make this straight. I think that's straight enough. It's okay, Diman. That's why we're here. That's why we're going over the answers, right? Yeah, so we'll start in around, I want to say 3 minutes. All right, so sit tight. Oh, right. Who's that? Thank you, Justin. Keeping things fresh is definitely one way of looking at it. The more realistic answer is I'm figuring stuff out too. All right. Do I drink matcha? Sometimes. It's very labor intensive. So today I'm brewing a brand new tea. It's a sencha from the Uji region of Japan. Look how delicious. Its leaves are very vibrant green, but the liqueur is golden, actually. And it's 10:01. Let's start. All right. So first of all, let me just pour a cup here, so you guys can see. Oh, look at that golden color. It's beautiful. I wish you guys could smell this. Maybe if we do see each other by the end of the year, I'll brew a lot. I'll brew like a gallon or something. I'll try and bring it to school. How about that? Oh, Dimon, a tea bag? You gotta educate yourself, buddy. Let's get started. Yeah. Hi, Toon. Chris. Uh, who else was here? Sarah. It's good to see you. Maya, are you in here? Huh? Okay. Let's get right to it. All right. So number one, at a strange place in space, a single alpha particle passes by every 3 seconds. So what is the current at this point in space? All right. So there's a lot of ways you could do this. All right. The most simple way is just to look at. Oh, sorry, I just moved the thing, but yeah. All right. So the simplest way is to. Hello. Can you? Not now. This is embarrassing. Come on. You gotta work for me. Okay, there we go. All right. So number one, we have. You're going to use the formula current equals Q over change in T, all right? And if I want to say my time interval is 3 seconds, then all I have to do for the charge that passes by in 3 seconds is 2 times 1.6 times 10 to the negative 19 coulombs, right? But just know that you could have used almost anything else, right? You could have also used, let's see, like if you chose a 6-second interval, for example, right? Then you could have done 4 times 1.6 times 10 to the negative 19 coulombs, right? So you could have theoretically picked almost any time interval that would be convenient for you, okay? And whatever you do, right, your answer is going to be around 1.07 times 10 to the negative 19 coulombs per second, or 1.07 times 10 to the negative 19 amperes, right? Those are the acceptable units for charge. I mean for current. Thank you. Yeah, guys. I know while I do the solutions, a lot of your questions will be answered, but I really like seeing you answer each other's questions. It's really good to see, right? Not just for like earning participation points, but it shows me that you guys care. Makes me really happy. Thank you. Yeah, you abbreviated with a capital A, right? All right. So moving on. Inside a copper wire, it's not uncommon to see up to 3 milliamperes of current. How many electrons would travel through this wire in 4 seconds? All right. So again, we basically have the exact same formula. I have I, the current equals the charge that passes times over the amount of time it takes. And right now I know this is 3 times 10 to the negative 3 amperes or coulombs per second. And I know that this is Q over the change in time, and I'm asking how much charge passes by in 4 seconds. So this is now I can say that the charge is, in 4 seconds, 0.012 coulombs. But I'm asking in right, so what is the type of charge that's flowing, right? For number 1, it was like a random 2 protons always passing by in space. In a metal wire, the current is carried by moving electrons, right? So now I want to say, okay, if I know 0.012 coulombs pass by every second, I actually want to see what that really means. And I want to say now, wait, so how many electrons actually pass? Then I just have to divide the charge by the charge of the electron, which is 1.6 times 10 to the negative 19 coulombs, right? Caitlin raises a good point. It should be negative. So um, that would be equivalent to saying that negative 0.12 coulombs passes by, and yeah, something like that. We're really just kind of focusing on the magnitude for now. All right. Yeah. So if you keep everything positive, it's pretty cool. Just know that if I have 0.012 coulombs traveling in this direction, that's the exact same as negative 0.012 coulombs traveling in this direction. I haven't even told you about the direction of the current, so it's cool just to put everything in terms of the magnitude. Okay? All right. And if I do this, I end up with 7.5 times 10 to the 16 electrons. It's a huge number. Okay? Current can be negative. Yes. But for the purposes of our class, you can always kind of think of it as positive, almost like force. Like I only want you to think about it in terms of like its magnitude and then its direction. And the magnitude is always positive. Okay? Current is not a vector though, all right? So that's also a very important thing. It is not, Yona. All right. What is the current in a wire if 3.4 times 10 to the 19 electrons pass by a point every 60 seconds? All right. So, just for good practice, everybody, right? It is always good to write out the formula that you're using, right? Rather than just plugging it in directly. I know it's like it can seem like a waste of time sometimes, but it's really good practice. All right, and this is going to be 3.4 times 10 to the 19 times 1.6 times, and I'm using positive, right? So that can be a little confusing, but I hope you know why I'm doing that now. Okay, and this is all over 60 seconds. And once I plug all this in the calculator, it is around 0.09 amperes or coulombs per second. Okay. All right. Moving on to number 4. Right. I hope these are all really basic. These are definitely, I would say, very close to Regents level questions. All right. It can get a bit more complicated, and it will. All right. So for those of you looking for a challenge, don't worry, it is coming. Okay. If it's 2 amperes, how many coulombs of electric charge pass by in 1 minute? This is just a test to see if you can convert from minutes to seconds. All right, so I have I equals Q over delta T again, and I have 2 coulombs per second equals the charge over 60 seconds. So the charge that passes by is actually equal to 120 coulombs, right? Did I say, hey, how many protons is it? How many electrons is it? No. So this is actually a much easier version of number 2. Excellent. All right. Moving on to number 5. All right. This is going to be a pretty short video. The current in a wire is 4.0 amperes. The time required for 2.5 times 10 to the negative 9, to positive 19 electrons is how much? I don't know. We're going to calculate this formula again. This is I equals Q over delta T. And I'm putting, you can do this a lot of ways. You can solve it like delta T equals Q over I, right? I don't really care, right? There's like a lot of things you can do. Basically, there's 3 givens. I mean, there's 3 variables. You have 2 numbers. And you don't really have to convert anything except the charge is equal to 2.5 times 10 to the 19 times 1.6 times 10 to the negative 19, or negative 1.6, right? Like it's, yeah, this number you can change. Yeah, right, so that's like the only thing you have to do. And I think the answer actually turned out to be 1 second. Very, very convenient, okay? Yay! All right, now let's move on to the juicy stuff. A piece of aluminum wire is 1 meter long and has a cross-sectional area of 1 millimeter squared. What is its resistance? All right, well, you're just basically using that little reference table I've given you. R is rho L over A, new formula, get pumped, okay? And here we go. What are we doing here? The rho is 2.82 times 10 to the negative 8 ohm meters. The length is 1 meter. And the cross-sectional area is 0.001. Whoa, 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 whoa. 0.0001 meters squared. All right, that's the big conversion whoopsie daisy a lot of people will do. Okay, like a millimeter squared is really tiny compared to a whole meter squared, right? I can fit a million square millimeters inside 1 square meter. Okay, that's what this is telling you. And the answer is 2.82 times 10 to the negative 2 ohms, right? So this is a pretty low resistance, which is good. We like our wires to have low resistance, right? Now let's move on to number 7. A meter-long wire with a radius of 1 centimeter has a resistance of blah, blah, blah. What material is it made out of? Oh my gosh. So this is cool because you first have to solve for the area. The area is pi r squared, which is pi times 0.01 meters squared. So this is equal to 0.00, give me a second, 0.314 meters squared, right? And then after you do all that and you plug in 2 for the length and then 1.8 times 10 to the negative 4 ohms for the resistance, you will get that the rho value for this is around 2.82. And oh my gosh, I hope that's super familiar because that's exactly the rho you used in the previous problem. So this wire is made out of aluminum. Hooray! Okay. Let's move on. This might seem a little easy. I think it is, but I really want you guys to stay tuned because I'll be introducing a second assignment. You guys are going to get a live preview of it right now. I will post it like a textual version online, okay, through Google Classroom. But yeah, for those of you who are fortunate enough to stay here online live with me to keep me company, because my only company is this cup of tea. I appreciate it, and I want to introduce this assignment for you. Okay. All right. So here we go. If both wires are the same length and are made of the same material, which would have a larger resistance, the round or the square one? Okay. Well, you don't. I mean, so for this is what, number 8. Um, if R is rho L over A, and I know they're the same material, the same length, it's just whichever one has the smaller cross-sectional area. And if I have a square and it's 1 centimeter side, and I have a circle that's 1 centimeter as a diameter, it's very clear to see the square has a larger cross-sectional area, right? What do these wires look like? I don't know. That's the circular wire. Here's my little rectangular prism. I hope we all know how to draw those from our art class, right? Would you ever make a wire like this? No. Mr. So, you're so funny. Lamau, LOL. Haha. Okay. Yeah. So, do we ever need to memorize any of the resistivities? Caitlin, no. You'll always be given a table. It's kind of like mu. Like, I don't think I ever gave you a mu value to. Thank you, Sylvie. Thank you, Alex. Oh, Becky. Yeah. So that's that. Yeah. So it's clear to see that the square wire has a lower resistance. Okay. Why don't we always make wires like squares then? Because it's actually not efficient to make them that way. Yeah, and if you're, yeah, it's just not good. All right, so 9. You could have also manually calculated the area. Like for the square, it would be 0.01 meters squared. For the circle, it would be pi times 0.05 meters squared, and you'd see that this is still smaller, right? Okay. I'm noticing my handwriting's tilting up a little bit. My apologies. That's totally my fault. Yes, you would want lower resistance in the wire, but this is no good because if you, how do I put this? It's just very difficult to manufacture that shape. So instead of making a square, you'll just make a bigger circle wire. Yeah. Okay. 9. A salesman is trying to convince you to buy gold wires because they lose less signals because it's a pure metal. Why is he wrong? Why is the only metal that would perform better than what is the only? So he's wrong because gold has a higher resistance. And the only metal with a lower resistance, resistivity, is silver. Why don't we use silver? Why do we actually? Well, why are some really high-end electronics plated in gold then? It's because gold doesn't tarnish, and any kind of tarnish, like rust or oxidation, severely increases the resistance, right? So the 2 metal alloys that resist tarnish the most, I think, would probably be gold and stainless steel. Stainless steel is a mixture of iron, cobalt, chromium and nickel. But iron itself has a very high resistivity. So you would really want to only use gold. There are other reasons for using gold too, right? Number 9 is supposed to highlight just how lucky we are in that we have a material like copper that has a low resistance. And we're lucky that copper is abundant and relatively cheap. Otherwise, our circuits would be really expensive. Like if there was, let's say if copper had a very high resistance, then we would be forced to make our circuits with silver. because those are like the only two metals with like a sufficiently low resistivity. Or we would make our circuits with silver, or we would make our circuits with a non-optimal metal, and all of our electronics would just perform a lot worse. Okay? All right, 10. Long wires are made of copper and made to have a thickness of 5 millimeters. That's pretty big. Like, that's like, that's around half my pinky, right? If you can imagine a wire as thick as half of your pinky. It's very thick. There are some wires even thicker than that. One such wire has a resistance of 0.023 ohms. How long is it again? Right? So I'm not even doing number 9. Right? We just like went over that for a while. I'm using the exact same formula. R is rho L over A. And if I do that again, I should get, once I plug in everything, the hardest thing is to get the area. This is pi. I've already given you the radius. Oh, I've given you the thickness. So again, you have to find the radius, which is 0.0025 meters squared. All right, and boom, you should get that it's 105 meters, right? The length would be 105 meters long. Cool. All right. Any questions so far before I introduce the, this is like a mini project. It's like a written assignment. So it's not a worksheet, and this one is due Friday, all right? I think it's a really cool thing. Okay, so we can get right to it then. Let's get right to it. Here is, you're confused on the last one. All right, I can show you my work total. It's 0.023 ohms equals, what was copper? Was it 1.72, right? 1.72 times 10 to the negative 8 ohm meters, L over pi 0.0025 meters squared. And if you solve for L here, you should get 105 meters. Huh. I don't know. I guess that's just the calculator thing. I mean, well, what did you get, Sarah? Dimon, what's so sad? Wait, Kyle, so you got the same numbers? I mean, wait. Oh my gosh, look at that, Kyle and Yana. You guys are off from each other by factors of 10. All right, let me do this again on the calculator. Okay, did you guys know that your physics teacher doesn't have a calculator? I don't own a calculator. I just always use wolframalpha.com. Super great. So I have 0.023 times pi times 0.0025 times 0.0025. Yeah, I do it the long way. And divided by 1.72. Oh goodness. Times 10 to the 8th. So I'm getting 2.625 meters now. Can I get a big yikes in the chat? Okay, now actually I get 26.25. That is the answer. My bad. I don't know why that happened again. Yeah, I got the same answer as Yona this time. Whoa, all right, so L is 20. Everybody makes mistakes. Everybody has those days, okay? 26.26. Yay, so it's a pretty long wire, okay? All right, so now I want to introduce to you a new concept, and it's related to resistance, okay? But different, right? So when we're talking about resistance, right? And I'm looking at this section, right? Resistance is a measure of how much I resist current or moving charge, right? So the more resistance I have, the harder it is for current to move. There are many different types of resistance, right? So the formal term for this is actually called electric resistance, all right? I want to take a really short journey into thermal physics. Because let's say I have a material here, okay? And I put this end over a flame. Hot, 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 hot. Ow, hot, 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 hot. Right? If I touch this end right here, right, with like my pointer finger or something, right, it's not going to be hot immediately, right? But eventually your finger will get pretty hot, right? And it'll hurt, it'll burn, right, if you're not careful. So why is that? It's because the heat here, right, it travels in this direction. And certain things cause the heat to travel a lot faster, and certain things make the heat travel much more slowly. This is just like resistance. This is called thermal conductivity, or thermal resistance, right? So this is the exact same thing, except instead of the movement of electric charge, we're talking about the movement of heat, right? And I'm going to tell you right now, it follows almost the exact same formula, right? So like my thermal resistance is just, you know, some rho, right? L over the cross-sectional area. So this is really important this has many applications. One of my favorite applications is cooking, right? So there are a lot of recipes, for example, that require you to start something on the stovetop, right? And you cook it in a pan like this, and then you move the pan into the oven, and you finish by baking the dish after you've kind of seared it off here, all right? And a lot of pans are made so that the handle, right, they change the rho value of the handle by making it into a material. They make the handle of a material that's very resistant to heat, that has an extremely high heat resistance, like silicone, right? So a lot of you have nice rubbery grips on the handles, or because rubber is a pretty good insulator of heat, or they'll be made of wood. Wood is a really great insulator of heat. It almost doesn't allow heat to travel at all, right? Assuming it's not moist, okay? So the problem with that is those types of pans, exactly, very high specific heat capacity. The problem with those types of pans is that, and this is not the exact formula for thermal conductivity. Yeah. Well, I think it's very similar. The problem with those handles is that when you put them in the oven, they'll burn. So a lot of pans, you'll notice they'll be labeled they're not oven safe, right? Because if I bake a silicon handle, or if I bake like a rubber handle or a wood handle in an oven at like 500 degrees, that thing is gonna burn, and like your whole kitchen's gonna be engulfed in smoke. So the only real oven safe pans are those that are entirely made of metal, like this one. All right. The problem with that is, if you guys can imagine, right, if I'm cooking here and this flame, the whole thing's made of metal, the whole thing conducts heat. Eventually, the heat, if this pan is really hot, then this handle's going to get hot, and the heat's going to travel and travel and travel, and then eventually this will get really hot, right? So like when I cook, I like wrap this in like cloth or something, and I hold it like this. All right. But the cool thing is, for most stir fry, like most like um, frying applications when you're on the stovetop, as long as you cook it under 10 minutes or so, or 20, like 15 minutes, the handle won't get hot at all. Why is that? It's because it's made of iron, first of all. And iron actually has an extremely high specific heat capacity and is not a very good conductor of heat. It's actually not a good conductor of heat. So by making the handle made of iron, I choose a very high, I choose a really high rho. This is a large value. And if you notice, if the handle is really long, it'll take a long time for the heat to travel back to my hand. And I make it thin as possible. I make it really thin, and that also decreases the A. So it takes a really long time for the heat to travel. All right. And if you have a very well-designed pan, for instance, like they'll always make it around here very thin. They'll make it as thin as possible. So it's really hard for the heat to travel all the way up. Okay. That's some cool physics for you. All right. And the other application of this would be, you betcha, teapots. Okay. Obviously, teapots get really hot. You're going to put boiling water in them. This is really not pleasant to touch a lot of the times. This is a Japanese style teapot with a handle on the side. If you're ever curious as to why they look like this, it's so when you hold it on the side, you can put your thumb on the lid while you pour. So it keeps the thing. You can imagine if I have a traditional Western grip, I can show you one of those too. I have one. One of these, okay, and you're holding it like this. It's much harder to do this. And it's like an awkward motion of the wrist, where this one is much easier, and you're just literally rotating your wrist, and that's all you have to do. Here, you're kind of doing this, and you're like tilting. It's not cool. All right, but there's a beauty in these as well. But if you're talking about thermal conductivity and stuff, if you notice, all of the handles are really hollow. These are hollow, which means the cross-sectional area of this is actually really small, right? It takes a long time for the heat to travel because these walls are really thin. So it's really hard for the heat to really travel all the way up here. Now, if this was made of solid clay and it wasn't hollow, right? This was solid, then the heat would travel really quickly. But because it's hollow and it's made of these thin walls, it takes a long time for the heat to travel because of the cross-sectional area. Likewise, that means when you make even a teapot in this style, what you really want to be aiming for is to make your handle as thin as possible. So it takes a long time for the heat to travel up here and up here, right? If it's a thick handle, then it'll travel really quickly and the handle will get hot, okay? The last thing I'll talk about is a little less, it's not G, it's not PG, it's kind of PG-13. The lids are hot. You know, there's no way about it. Like, I don't know. So, but also the lids aren't really in contact with the water, so they're just kind of like absorbing the thermal energy of the steam. So it's really not that hot. Okay. The PG-13 example I like to do with this is grape juice. Okay, fermented grape juice. If you ever wonder why grape juice glasses are shaped like this, it's not because they look elegant and people are trying to be classy. And that's like, why do we make drinkware or glassware with stems, right? What's the point of a stem? Is it to look classy or anything? No, it's because grape juice is typically best enjoyed at around room temperature, right? And room temperature is around like 20 degrees Celsius, okay? But the problem is your hand is a lot warmer than that. Your hand's around, right? Your hand is around 27 degrees Celsius or 29 degrees. Does anyone know your body temperature? Let me look that up. Oh, your body temperature is 37 degrees Celsius. Yeah. And I think room temperature is actually sorry, room temperature is not 20. Oh, it is. All right, yeah. So your hand is much hotter than the wine. I mean, oh, the grape juice. Grape juice. And so the problem with this is like if you pour grape juice into if you pour grape juice into a standard cup like this, right? And you hold it with your hand, you're going to heat up the grape juice, right? Your hand's directly like heating up this thing and it's gonna taste awful, okay? So our goal is then to put it in a glass like this and then to hold it here. Because if you hold it here by the stem, then you're only heating up this part. And in the chat, can you tell me why, if you hold it here, this necessarily won't heat up? Or it will, but it'll take a very long time for it to feel the heat. Why is this in the chat? Exactly, right? It's thin. It has an extremely small cross-sectional area, which means it's really hard for the heat to travel all the way down here, all right? Not only that, it's long. Yes, Sarah, right? So grape juice glass manufacturers now have a very real conundrum, right? Because the ideal would be to make this as long and thin as possible, but you know what happens then, right? It's really easy to break. So they have to really they have to take a lot into consideration when designing stemware like this, all right? And this is why if you ever see someone hold a grape juice glass like this, oh, look at this. Oh, this is so bad. right? This is defeating the entire purpose of what engineers have done to design this thing. Never hold your grape juice like this. All right, this is extremely, extremely dumb. All right, I can't think of it, but yeah, you gotta hold it like this, right? You gotta hold it here. You gotta use it the way it was meant to be used. Okay. Also, these have become quite trendy, right? They're called stemless grape juice glasses. For reasons we already know, these are pretty dumb, right? I mean, the good thing is they save space, right? Like storing stemware is a real pain in the butt because they take up so much space in your cabinets, and that's what these are for. These also fall down a lot less easy, right? This is tall; it can really fall and stuff. This one, it won't really fall, right? But also, it's terrible for thermal conductivity and stuff. Why do you own one then, Mister? I don't talk. Don't ask questions. Okay. All right, yeah, so I'm basically going to ask you to explain like why the design of a grape juice glass makes sense, knowing what we know about conductivity and stuff. What would your ideal grape juice glass look like if you were to design one? And also to find another example where something like this is used, besides like a teapot handle or something like this. Like, where else do you see situations where we actually want to increase the resistance, right? Isn't that weird? Like, so that's the other thing, right? Like, this is a an example of where I want to increase the resistance. How cool is that, right? Where like for the electric resistance, we were always looking for things where we're trying to decrease the resistance. All right. All right. And with that, I will let you go. All right. I hope you guys have a wonderful rest of the Tuesday. I will send this little more fun writing assignment tonight, as well as the worksheet that will be due for after tomorrow's lecture. All right. Okay. Also, why is it in the movies that the stereotypical elegant character? I don't know, Chris, but it's terrible because it's setting a terrible example. Um, yeah, you should basically. I mean, the lesson you should be learning from this, Chris, is that you should never be looking to movies for examples on how to do anything, right? Movie romances are terrible things to model your own relationships after. Um, Superhero movies are like terrible representations of how to solve a crisis, and movies where elegant characters hold the wine glass like this are a terrible way to learn how to hold a grape juice glass. Okay, and why do they? I have no. Oh, that I think is a right, Dimon. If you think about it, the fewer fingers that are in contact with this, the less heat you're giving to the stem. So that actually kind of makes sense. I don't know, right? Have a great rest of the day. All right. See you guys tomorrow.